Hi, my name is Linda. I'm a children's book author, a storyteller, an illustrator, a programmer, and my work happens at the intersection of three different things. Early childhood education, where I draw my inspiration from the likes of Montessori, Reggio Emilia, Piaget, in the technology field, where my biggest idols are the optimistic superheroes of the 60s computer science research culture. And finally, play and creativity, where I explore the softer, more communal, more subjective side of learning that often gets overlooked. And here's the thing about us humans. We contain multitudes. We can be many things at the same time, work at the intersection of many different things. And that's not what happens with computers. They are binary. They are zeros or ones, on or off. Binary little creatures. But we humans can be many things at the same time, and that's what makes us so special. This is where I started my author journey. I figured that if coding is the next lingua franca, if our kids are going to be learning English, Chinese, and JavaScript in schools, instead of grammar classes, we ought to be teaching them poetry lessons. And what I mean with that is the idea that I didn't learn Swedish by only doing jag heter, du heter, han heter. Rather, I learned Swedish by speaking it, by singing it, by flirting with nice Swedish boys in it, by reading books, by writing letters. And even though programming is not a natural language, I think the ways we teach it ought to have much more diversity in it. And one wonderful way to teach is through stories. So when I was beginning my computer science career, I too ran into these dull, gray, big computer science books that were full of jargon, and I would scratch my head and feel overwhelmed and think, oh my goodness, what is object-oriented programming? What is HTML5? What is garbage collection in mobile development? And the language I was practicing at the time was called Ruby, so all of a sudden, in the margins of these boring books appeared a little girl character who started to explain to me what is object-oriented programming, and I kept drawing her character all through my CS books, and something in my brain irrevocably switched. You see, there's people who see numbers as colors. I started to see the world of technology as stories. And I figured that, okay, Ruby is one thing, but what if Apple was a character? It would be the snow leopard who's beautiful but doesn't want to play with the other kids because they are way too messy. It only likes well-designed, nice things. And then there would be the androids who are really messy, and there's a ton of them, and they grow up a little bit too quickly to be dependable, but they are really friendly. And there would be Linux the penguin, who's really book smart and efficient, but somewhat hard to understand. And I went to my mom and I tell her, Mom, I want to leave university. I want to write stories about the world of software. And my mom tells me, Linda, that's a terrible idea. That sounds like a Soviet propaganda book from the 70s. That's the books I grew up reading to. Why should kids understand how big technology companies think? Well, the reason is religions barely reach billions of people. Countries don't reach billions of people, but technology companies like Alibaba, Rakuten, Facebook, Google, they reach billions of people on a daily basis, and it really matters what kind of value systems we have built inside of them. So that's why stories. And we live in this era of amazing opportunities to learn to code, everything from code.org to the open-ended playground of Scratch. But I think there is a tendency for us humans to understand ourselves, each other, and the world around us through stories. And that's what was missing from computer science education field. And being here in Sweden, I can't think of a better audience to appreciate this next story. It starts from the 70s, and you all remember when one of your most beloved children's book authors bought the front page of Expressen and wrote a story about Pomperipossa and about taxation, and that was obviously Astrid Lindgren, who famously said that politics is too important to be left for politicians. And I think the ethos for the 21st century is technology is too important to be left for technologists. And that's why I think work like this matters. So I write children's books physical, real books that have been translated into a lot of languages. I don't only write about coding, that's maybe the thing I'm most known for. I write also about computers, the hardware side of things, and I write about how computers talk to each other, so what is the internet? And I write about how computers are changing the society, namely what is AI and machine learning. But most of all, I try to explore the world where more and more of the problems around us, they are turning into computer problems. And we need a radically more diverse group of people to see computer science as exciting and fun and whimsical. And there is a big chasm we need to break in our head. Because when we think about a physicist, it's easy to see that, a physicist is a person who studies the physical world. And when we think about a biologist, it's easy to see that, a biologist is a person who studies the biological world. But when we think about a computer scientist, we leap into the assumption that the computer scientist is the person who studies the computer. No. Computer scientist is the person who uses the computer to solve the big problems in the world, those of nutrition or health or education or energy. And we need a more diverse group of people to see computers as a tool of self-expression, as a tool of problem solving. Because computer science, famously, is no more about computers than astronomy is about telescopes. It's about thinking skills and it's about practices. And with that in mind, I want to give you 3 ideas to take home with you. And because I'm a storyteller, they are going to be coming in the form of A, B, and C of technology education I wish my future children would have. But before we get into that, I need to introduce you to someone. And this little someone is a fierce 6-year-old. Her name is Ruby. She's a little bit bossy, very imaginative. And when Ruby's dad tells Ruby, we're running late from school. Please, please, please dress up. Ruby dresses up, but she leaves her pajamas on because Dad didn't specifically tell her to first take off the pajamas. And when Ruby is told, Ruby, your room is a mess, clean up all the toys. Ruby puts the Lego blocks away, she takes the plush toys away, but she leaves the pens and papers on the floor because, come on, Dad, pens and papers are not really toys. And there's a chance I'm raising the most obnoxious generation of kids ever. I apologize for that in advance, but they also learn something very profound about how to speak to a computer. Namely, you need to give very exact commands in the right order, you need to be careful when you name things, and you understand that even the biggest problems in the world, after all, they are just tiny problems stuck together. And with that, I want to take you to the first letter, which is obviously A for an algorithm. One activity I do quite often with kids is this one, where I ask the kids to write instructions on how to wash your teeth. And the results vary. There's never one specific algorithm they write. There's always mistakes they make, like how do we know what a toothbrush is? Keep moving your hand towards the toothbrush. Did you remember the toothpaste? Did you remember to take the cork off the toothpaste? And through an activity like this, the kids actually learn something even more profound about coding than writing the actual syntax. They learn that programming is done together. 2 pairs of eyes or 2 pairs of brains spots problems better than one. They learn that programming is all about making mistakes. There's never perfect code at the first get-go, and it's a lot about just practicing and trying things over and over again in a different way. And they learn that there's as many answers as there are programmers. This was my pet peeve growing up. I hated it, that in my computer science classes there was only one right way to solve a problem. That's math, that's not computer science. And they learn that algorithms, after all, they are just step-by-step instructions to solve a problem. So if you want to make fancy macarons or cupcakes, you're actually following an algorithm. If you give instructions for someone to find your place, that's an algorithm too. And at this point, some of you might be thinking, that's cute, that's nice, but this doesn't really have anything to do with the real world of computer science, the numbers and the hard stuff. Well, you need this basic framework in order to understand the next example, step-by-step sequences to solve a problem. Because when a computer is given instructions, it can repeat the instructions endlessly over and over again without ever making a mistake. And here's an example. So if I asked kids to put these 5 numbers in order of magnitude, it would take them roughly 10 to 15 seconds. If I asked them to put these numbers in order of magnitude, it would take them a little bit longer, and even longer for these ones. And to their disappointment, I tell them that, for a computer, this would be trivial. A computer will always beat us with tasks like this. But it still needs instructions. So the way a computer would approach a problem like this is this. It would start from the beginning, it would compare 1 to 56, it would decide, 56 is bigger than 1, let's keep it like this. It would move on, compare 56 to 4, it would be, let's swap them around, 4 is smaller than 56, let's move on, 56 to 70, that looks fine, 70 to 20, let's swap around, and then let's go to the beginning and do this whole sequence over and over again. This is called a bubble sort algorithm. This is a really famous algorithm someone wrote in the 50s or the 60s, and it's still in use in computer science almost in every single service we use. It's an algorithm that a human created, a step-by-step instruction to solving a problem. But this, to some of you, might be too theoretical. What about the algorithms we think about when we think about the word algorithms, like the scary Facebook stuff and the world of finance? Well, I show kids a picture of a search engine and I ask, where is the algorithm hiding, like a traditional kids activity? What about the ads you see? That's the algorithm in the works. What about the order of the search results you see? What about a social networking site? If you go to a boy's profile and watch it over again, the algorithm will recognize that and show it to you more often. Again, the ads. And then I show them YouTube, and then we have a discussion about how does YouTube learn about what you want to see next in your feed. That's an algorithm, or what kind of ads you want to be shown. And regarding James's work, I think it's a really fascinating world that we're living in, where the algorithms are not only choosing the kind of content we're seeing, but also creating the content. And I think making and unveiling these black boxes is one of the most democratic things we can offer to our children. None of this is actually news. If we were to talk to educators, they would be able to tell all of this is old news. Because already in the 60s, Jean Piaget famously said that you can't offer an entirely organized intellectual discipline for someone. Rather, true learning is grounded in action. And computer science is often full of pre-organized vocabularies of content. We transfer meaning, we don't make meaning. And this is a problem. And another problem in the way we teach is that we focus on such a narrow understanding of what playfulness looks like. We need to say hello to our friends in Denmark, where Lego has been doing a lot of groundbreaking work throughout the years in understanding different motivations for play. And this is one of their charts where they mapped 3 basic motivations for play. They say there's achievement-based motivation, social motivation, and immersion motivation. But for some reason, whenever we talk about gamification and making education playful, we focus on this achievement box. We talk about domination, about challenging others, about points. And in reality, everyone here who has ever programmed knows that there's so much more in learning. There's the joy of giving and getting help. There's the joy of finding a new way of solving a problem. And at least for me, there's often the joy of just escaping my own real-world problems when I'm programming. So rather than saying that we should only teach using a narrow idea of play, let's use all of the different aspects of play. And let's ask questions that the computer science industry doesn't ask. A typical question a computer science professor might ask from a university student would be something like, could you define to me what a loop is and write an example of a loop? What if we asked questions like, how does a loop feel like? So a loop is a construction very central in the world of computer science. The idea that a computer is repeating instructions over and over again, but it needs instructions to know what to do. And in Ruby's world, we practice the concept of a loop by having a dance party, where we first go clap, clap, stomp, stomp, clap, clap, and jump. And I practice with the kids first by doing a for loop, which is one type of a loop, where we repeat the sequence of dance movements 5 times. And then we do a while loop, where we repeat the dance sequence while a condition is true. So while I'm standing on one leg, the kids keep dancing. And then finally, as homework, they get the until loop, which is the funniest one, because you keep repeating the dance sequence until mom gets really, really frustrated with you. And in this way, I hope the kids will get to climb the abstraction ladder of computer science, starting with the kinetic, starting with the physical, then maybe going into a visual programming language like Scratch, then trying code, and very, very importantly, by understanding the context of what they are learning. Not only what is a loop, also how is a loop used, why am I learning this thing? And turns out there's this whole field of thinking behind these thinking skills and concepts and practices called computational thinking that we humans use in order to structure problems in a way that a computer can understand them. And often things like algorithms, decomposition skills, pattern recognition skills get listed as things that even primary school-aged kids can learn about coding. But I would want to highlight that the other side of things, these practices of persistency, of collaboration, of debugging skills are equally important when we teach. So that was A for algorithms. B is for Boolean logic. And it starts with the admission that I'm actually fairly envious for some of you. Because there's people here who grew up with the 60s and 70s computing culture. The time of the machines that were the size of this room and the personal computer revolution and the time when you could actually tinker and twist and turn around your computers. That was a time when you could actually touch a transistor. My generation, we can jump 300 million transistors at the pinpoint of a pen, but we have no idea how computers work anymore. They are sealed boxes from us. They are these magic devices, and they've become very abstract and very foreign. And sometimes I just wish I could shrink myself to the size of a silicone chip and kind of go inside of a computer and really learn how it works. Unfortunately, with modern day physics, that's not possible unless you're a children's book author. So that's exactly what I did. One day, Ruby is really bored. She goes into Dad's study, she types her password in, but the computer doesn't work. And all of a sudden, the white mouse, it wakes up next to Ruby and says, Ruby, Ruby, I've lost touch with the cursor. Can you help me find the cursor? And Ruby says, of course, I'm the best computer debugger I know of. And together, just like Alice in Wonderland, they fall deep, deep, deep inside of the computer to the layer of the electricity, where there's billions of tiny switches that only know how to go on and off, on and off. And Ruby is impatient, and she says, it's going to take forever for the switches, these little bits, to give us any answers. Up we must go, and up they go until they meet the logic gates that take these tiny bits and do a little bit more complicated mathematical operations with them. But they are no use either, so up they must go until they meet the hardware layer of the computer, where there's the CPU of the computer, the bossy processor that says, fetch, execute, store, fetch, execute, store, but forgets stuff easily, so it needs help from other components. They meet the operating system, and I'm not going to spoil you how they find the missing cursor, but they do find the cursor. But I think even more importantly, the kids learn how electricity turns into logic, how logic turns into hardware, how hardware turns into software, and how software turns into the apps, operating systems, and programs we use every single day. And very, very importantly, they realize that while computers are magical, they are not made of magic. They are made of logic, and it's a big distinction in our heads. One of my favorite activities around the idea of a computer is this. What if computers don't look like the computers you and I know for much longer? What if the next generation of kids is actually having discussions with a computer? How do we teach what a computer is in this era? And I think it starts by building a mental model that starts from your own experience. And I ask kids who are usually between 6 and 9 to draw what they imagine is inside of a computer. And I've collected pictures from kids all around the world, hundreds of them. And there's a bunch of different categories you can kind of outline from this data. There's definitely kids who see computers as content containers. They imagine that inside of computers there's files and there's apps and programs, and they are right. This is what a computer for many of us looks like. There's linkers. There's kids who have this very abstract network idea of a computer where they draw these components and their relationships. These are the future computer architects in the making. They are right too. A computer is an abstraction. There's the scenographers, kids who draw very intricate illustrations about the metaphors of what a computer is and how it's a theater stage and how each of the different components does its own thing. I have a personal affiliation for these kids because that's the way I understand what a computer is. There's even gear gurus, these steampunkish kids who think that inside of computers there's tiny gears that do complicated things. And they are not right. There's no gears inside of a computer, but they do grasp something very profound about how the basic operating unit of a computer does a fairly simple thing. It either passes electricity or it doesn't pass. But by combining and interlocking these units, computers become very complicated. And then finally, the drafters, the kids who draw currents, electricity, components. And I think having some sort of a mental idea of what a computer is inside, not just consuming content from a sealed box, gives a more democratic way of looking at the future. So computers as abstraction machines. One of the things that I worry most about is that my generation still recognizes a computer by the keyboard and the screen. But this is the last generation of kids whose computer will have a screen. The next generation will have a computer built into their toothbrush, some of us already do, into their teddy bear. And it matters what kind of people we get to build these products. So often I show kids pictures of a car, a grocery store, a dog, and a toilet. Keynote quit. The computers are like staging an uprising here. They don't like my message for sure. So I show kids a picture of a dog, a picture of a grocery store, a picture of a car, and a picture of a toilet. And I ask the 5 to 9-year-old kids, keep scrolling, down. I went through a lot of slides. Further down. Oh, you can open it up and actually I can just click through. Yeah, beautiful. So I show them these 4 pictures, and I ask them, which one of these do you think is a computer? And unanimously, the kids say, Linda, are you completely bonkers? None of those is a computer. But then we start talking, and we figure out that actually cars are computers because they have navigation systems. Many kids talk about self-driving cars already nowadays. Grocery stores, boy, do they have computers. When you walk inside of a store, the doors logically open up. The teller's machine is a computer. The ice cream box is a computer. Dogs might not be computers, but a lot of kids talk about robot dogs. And what if a dog's collar has a computer inside of it? That might be a good thing if the dog runs away. And then I tell the kids that, in Japan, toilets are computers, and there's even hackers who hack them. And this is like the biggest mic drop moment you can do with 6-year-olds. Nothing else gets discussed for the rest of the day. So we figure out that there's more than 2 computers in your home, more than the desktop or the laptop or the phone. There's hundreds of computers because your microwave is a computer, your toothbrush is a computer, your doorbell is a computer. And the next activity we do with the kids is this, where I give them a little tiny sticker with an on-off button on it. And I tell the kids that, for this afternoon alone, you have this magical ability to make anything in this room into a computer by putting the sticker on the object. And I've collected things like a lipstick and a book and keys. And then one little girl comes to me and she's chosen a bicycle lamp. And she comes to me and says, Linda, if this bicycle lamp were a computer, I could go on a biking trip with my father. We could sleep in a tent. And this bicycle lamp, it could also be a movie projector. And that's the moment I'm looking for. Not the moment when the kid understands the differences between hashes and arrays in Ruby or how to write a perfect if-else statement, but the moment when they understand 3 profound things about technology that I think we've been talking a lot about in these last few days. First of them is that the world is not ready yet. There's a lot we haven't invented or discovered. The bicycle lamp movie projector might not be the most important thing out there, but that still doesn't exist. The second thing is that even though technology can be scary, it's also a great way to create wealth. It scales. It's the way humankind has always advanced in the world. And then finally, the third thing she realizes is that for a moment there, she felt she had the self-efficacy, self-belief, and self-assurance to know that she very well could be the first bicycle lamp movie projector inventor. And I think that's the thing we should be supporting and safeguarding in our children, and also a little bit in ourselves. So how do you explain what a computer is then for this next generation? In order to do that, we actually need to travel all the way back to the year 1945, when computers were bigger than this stage. But the basic operating principle of what a computer is still surprisingly similar. We need to meet Mr. John von Neumann, who designed the von Neumann architecture of a computer. And a little bit simplified, what von Neumann says is that a computer is any device where you input data, you process that data somehow, and out comes modified data. And this is true when you go on Facebook and you like a post, in goes the like information that someone has liked this post to the Facebook server, out comes the updated like count. But this is also true when you sit in a car and you forget to buckle your seatbelt, in goes the sensory data that someone is sitting here without the seatbelt on, out comes the beep, beep, beep noise we hate so much. And turns out the world is full of data. The world is full of sensors. The world is full of us clicking everything online and creating this data. And that means computers have 1,000 faces. They have 1,000 forms. And by this point, kids say, you're too philosophical, let's do something. So we make a paper computer, and I hide inside these little pieces of code that say, for instance, come out jumping on one leg. And in goes the input data. One of the kids who crawls inside of the computer reads the code and comes out as the output data. And then the next one goes in, then the next one, and eventually this computer breaks. But they, again, get a very kinetic, very tangible, very real experience of what the input-output process looks like. And slowly, I've started to think that maybe the most important thing I do is actually not teaching kids about coding at all. Maybe the most important thing I do is giving them this very robust mental model of what a machine is good at and what a human is good at. And maybe that's the skill we ought to be focusing on with the next generation, giving them the idea of a notional machine. And that brings us to our final topic, C, which is for creativity and computers. So there's been quite a lot of talk about AI and machine learning. And the moment we talk about these things, something happens to us adults. We start to talk about medieval monsters, something that is the unknown, the Terminator or the Skynet, and we start to project our own fears to our children. And that's not fair. So what I would rather see is an optimistic and pragmatic generation of kids who are not fearful about AI, who feel empowered to change things and understand the black box. So what I'm going to do next is try to explain to you guys what machine learning is in the same way I would do with a 6-year-old. So the world is awash with data. We generate a lot of data. Some of it is behavioral, some of it is big, some of it is incidental. But all of a sudden, there's much more data in the world than there used to be. All of a sudden, there's also much more computing power than there used to be. And all of a sudden, we share much more information as a computer science industry because of the internet than we used to. And all this means, all these three things mean that things that were discovered in the 80s, machine learning algorithms and techniques, they have become relevant again. This doesn't mean that computers are any closer to our soul, to our cognition, to our understanding, or to our to our humanity than they were in the 70s. It just means that computers have become better at mimicking certain types of tasks we humans used to think were only done for, belong to us. Things like seeing, sensing, things like reasoning, sometimes even things like creating. But this doesn't mean that computers are gaining singularity. It doesn't mean that they are gaining consciousness. What this means is actually this. In the past, if we wanted to teach a computer to recognize a cat, we would write intricate, detailed instructions of what a cat looks like. We would write a cat is an animal that has 2 ears and a tail, and it comes in these 5 colors, and then along would come Garfield, and the program would break down and not recognize the cartoon cat as a cat. And these instructions were brittle and broke down easily, and this is why this field of AI didn't move very far along. Instead, what we do nowadays is we give examples of cats to a machine. So this is always the thing that makes kids most anxious. The computer learns what a cat is by looking at YouTube videos for 10,000 hours and then generates its own rules. And the kids are like, why can't we do that? That would be so much more fun. So we humans ask the question, the computer gives the answer. We humans gather the data, we collect the data samples of things that are cats and things that are not cats. The computer builds a model that might not look anything like the model we use to understand a cat. We don't really know how we actually know what a cat is, so we don't know how similar the computer's perception is. And then it gives an answer. And very importantly also, it doesn't give an answer, it gives an estimation, it gives a percentage, it gives an idea of like, maybe this is a cat, maybe this is not a cat. And this process of asking a question, gathering data, and feeding back into that data and fixing the model is called machine learning. And when researchers talk about machine learning, they easily, or like not researchers, when reporters talk about machine learning, they easily say that it's a black box. Even researchers don't understand what is happening inside of the machine. And I think that's unfair, because we do understand what is happening inside of the machine to a certain degree. We are not able to explain every single thing that is happening inside of it, but that's an unfair statement that raises fear and anxiety in a group of people that don't deserve that, which is the kids. And maybe a neural network can be taught through a game where you collect from each layer of things the stuff that belongs to each of the vehicles. Maybe we can teach different algorithms by teaching kids that, hey, reinforcement algorithms just mean that the computer tries over and over again, just like you. And coming up with metaphors of explaining these black boxes, I think, is super, super important. But even more important is the data. Because that's where I think most of our non-programmer people, the people who don't see themselves as like the badass algorithm creators, will be dealing with in their future jobs. Often I show kids these 4 cats. And I tell the kids that if computers learn by examples, what is the bias that the computer is learning here? Maybe that all cats are gray and they have blue eyes. So can you design a cat that isn't gray and doesn't have blue eyes? Then I show them a picture where a computer gets 4 teacups and ask them to spot the bias here. And pretty quickly they realize that a computer wouldn't be able to recognize a teacup as something that has the handle on the left-hand side based on these examples. And these are pretty okay examples, not scary at all. But what happens when we automate more and more systems with the machine learning and AI algorithms and accidentally create a data set where all nurses are female? And this is why I think it's important to introduce these topics at an early age, where you don't yet define yourself in this binary manner of I'm a technologist, I'm not a technologist. And if there's one wish I could do about the future is that this next generation would remember John von Neumann, would remember the 1970s and understand that while self-driving cars are magical, they are not magic. It's the same input process output thing that was happening in the 70s. What a self-driving car actually does, it has car cameras that gather data, and the process is making a map of the position of the other cars, and then the outcome is the ability to drive. And very, very importantly, I worry about us getting a sense of what we humans are good at and what machines are good at. And this is where I think we need a lot of people to brainstorm better ways of doing this. One example is this. I ask kids to design their own algorithm. And by this, they know that, an algorithm is just a step-by-step sequence to solve a problem. So maybe my algorithm is to draw a big blue circle. Another kid's algorithm might be to make a green dot inside of each blue circle. And a third kid's algorithm might be to connect the green dots with a red line. And in roughly 20 minutes, we've created this beautiful piece of artwork. And I asked the kids, so how long do you think it would take a computer to generate an artwork like this? And the kids say, maybe it would take the computer 200 minutes to do this because there was 10 of us and we took 20 minutes. And I say to them that, a computer would do this in a nanosecond, probably a million of these, because this is exactly the kind of task a computer is good at. It's good at repeating sequences of instructions over and over again, faster than any human ever could. But how does this artwork make you feel? And a little girl raises her hand and she goes, "It makes me feel very busy." And another one says, "It makes me think of summer vacation we took with my father." And I tell them, bingo, those are things a computer can't do. A computer can never experience emotions around artwork. A computer is not very good at getting excited on behalf of us. A computer doesn't have memories of its own. A computer can't offer an interpretation about artwork based on its own experience. And these are things we humans will be pretty good at for a long, long time to come. So it might be that our kids won't write code. It might be that our kids, instead of doing the toothbrush exercise in the future with flowcharts, will be doing it by gathering examples of kids brushing their teeth. It might be that our kids in the future, they won't be writing JavaScript or Ruby, but they will be giving instructions to an AI and modifying, to make sure that these instructions are ethical and lead to the right thing. It might be that the farmers of tomorrow will have more time to smell the flowers and speak with the neighbors when the computer vision takes care of the bugs, or the future dentist will have more time to calm down the little patient when the AI spots the problems in the teeth. And I think all of this requires us to have a much broader participation in the field and discussions around AI. And one of the things I wanted to end my talk with is this exercise or example from Antoine de Saint-Exupéry, who famously drew a picture of a boa that had eaten an elephant. And he shows this picture to the adults, and they say, "Oh, it's a hat." And then he becomes really disappointed and says, "Oh, I don't want to talk about anything exciting for these people, like magical forests or stories or something like that. Rather, I would just talk about politics and neckties and boring things." But the kids know, the kids recognize immediately that it's a boa that has eaten an elephant. So if this is the dynamic between adults and kids, I was wondering, what is the dynamic between adults and AI? How could we work as a team together? And I fed this image to the Microsoft Vision Imaging API, and it tells me that I'm not entirely sure, but I think it's a close-up of a guitar. And this is the future of AI I'm really excited about, where AI is not only about optimization or efficiency or prediction, where we can be creative together and solve problems in a way that our perception doesn't allow us even to think about right now. Last story. There's this famous company in Finland where I come from called Marimekko that makes this bold, crazy graphic wear. And one of my favorite things to think about is, what if Armi Ratia, the founder of this company who lived in the 70s, was a programmer? How would have she projected her internal vision? And I decided to practice this. So I collected 1,400 examples of Marimekko clothes names, like Unikko, Jokapoika, you know the drill. And I fed them to a recurring neural network, and I asked it to produce new Marimekko names. And the first results were really disappointing. There were things like Valos, Inislö, Onasot, Ikkakunit. They sounded Estonian and not fun at all, and I felt like, maybe my dream co-worker of the future, the creative, crazy AI, is not as close as I wish it to be. But then I allowed the network to keep going for a little bit longer. And in the morning, I wake up, I feel like it's Christmas or Tamagotchi, or it's like a mixture of those two things. I go to see what the computer has created. And the results are beautiful. They are things like pyyninpakka, tanohalti, putti, pukukka, tirkka, ruitintullo. These things sound really Finnish, right? They don't mean anything for sure, but they grasp the sort of Karelian playfulness that Marimekko is known for. And I show this to the creative team at Marimekko, and they go really white all of a sudden. But I tell them that, the computer generated 1,000 of these, and I was needed still to curate and decide which ones to take. So this is the future of computing I wish to see. A creative, whimsical, colorful world where we all have agency and ability to describe what is happening around us. And this requires us to ask questions that we are not very used to asking, as mentioned. One time a little boy came to me and said, "Linda, is internet a place? And I start boldly explaining to him that yes, internet is an interconnected network of computers. It's an information superhighway where you go and surf. And I realize, oh shit, this is the 90s kids' internet. This is my internet. This is the metaphor I use to describe what the internet is. For this kid, he has never disconnected. He's always been on the internet, and I love in James's book where he talks about the metaphors we use to describe the technology around us. And I think this is one of those stories. So, is the internet the hardware, the fiber optic cables that go from the bottom of the sea all the way to the space? Or is it the protocols that govern how the data travels around the world 8 times in a second? Or is it everything that happens when the 6 billion of us are connected to one another, all of the cat memes and the funny YouTube videos? Well, this is the challenge with technology. It's all of the above. It's the hardware, it's the software, it's the societal impact, it's the history, it's the philosophy, it's everything. Because technology is built on humanity. Technology at its core is about us humans. That's in the definition, which comes from Greek, and it goes like this. It says, technology is tools to solve a problem. But not only the tools, also the skills and competencies we humans bring into the problem-solving equation. Today, technology is computer. Yesterday, it was a combustion engine. Before that, it was a bicycle. And we don't know what technology of the future looks like. But one thing we know, it's going to involve us humans. So I'm going to leave you with a definition from a little girl, a 9-year-old girl, who, when asked what technology is, came up with this answer. She says, technology is electricity that loves. I'm going to repeat that because that's the most poetic explanation of technology you'll ever hear. Technology is electricity that loves. It is used to play. I use it to have a conversation with my mom. We use a WhatsApp application. And then finally, and most importantly, people uses technology. Thank you very much.
Thank you so much, Linda. So, Neil Stevenson wrote a really lovely book called The Diamond Age.
I love it.
Yes.
Like the young lady's illustrated primer. It's my favorite.
There's an illustrated primer. There's a children's book, but this is in a nanotech future. So the book grows up with the child and teaches, and as you follow through it's complicated, but
it's Stevenson.
but it teaches. Ultimately, we realize it's been teaching her programming the whole time. And I thought about that when I was listening to you, and I thought about what James was saying, that the computer will never be able to explain to us why it plays Go the way it does. Do you think that's actually true? Will it ever? I mean, won't we do our utmost to build computers that can actually tell us things about their world?
I think that's one of the other assumptions the sort of media industry is doing out of their own fear, because already now I think, for instance, doctors are paying a lot of attention to AI that can actually explain its reasoning, because like a doctor doesn't want to take an AI's idea of what or like a prediction just out of the black box. They want to be able for the AI to be able to reason things. But that requires us as the public, as the sort of audience, to demand also for those things.
I wonder about these workshops that you do with kids. Do you ever do the exact same workshops with grown-ups?
I think best storybooks are things that speak to multiple different age groups, and in some ways the workshops work in the same way. I think that's one of the big problems of the tech industry also, that we take ourselves really, really seriously. And when you look at like a computer science book, it's really serious and it's kind of pretentious almost in its seriousness. And in some ways, children's books are a really wonderful way to like sneak some knowledge into the adults too. And that's the like you have basically the options of doing pretentious or doing like computer science for dummies. And no one wants to be a dummy when you're learning something new. So I wish there was a little bit more breadth to the way we adults also learn.
In the Lego presentation yesterday, there was a little bit of a flavor of this, that children, to children today, there's no really conceptual distinction between online and offline. And I feel ancient even saying that. But this is at the crux of what a lot of different industries are looking at now. I mean, 10 years from now, today's child will be a grown-up and a citizen and a consumer. And we don't know how they think about technology and how they interact with it. But I think maybe you know. What can you tell us that we should all know about kids and technology?
Yesterday I was doing this machine learning workshop with the 6-year-olds, and when I asked them to, like, how many of you have had a discussion with a computer? I think like 75% of them raised their hands, and I'm like, this is interesting. Like, the 6-year-olds are growing up in a world where they think it's very natural to converse with a computer, and I think that's going to have a very profound and big impact on how they grow up. Then another example, like just a sort of a storyteller's tidbit, I think it's really poetic that we live in a world where you will always have a leash home. So when I travel, my goddaughter follows me on WhatsApp and we send messages, and then I share my location. And wherever she is in the world, she will be able to kind of find me and find the distance between us. And there's a lot of these kinds of like societal and cultural like ideas that are baked into our technology that we ought to be researching more. And that's actually why the 60s computer science research industry is such a favorite of mine, because there's a lot of really cool researchers who studied this already then, like what is the perception of living and non-living objects in the 60s when computers were much more like jankier than they are today, and that research ought to be continued for sure.
What was it about the narrative of these technologists in the 60s and 70s and their view of computers that you love so much?
Favorite thing for me is the fact that they like randomly appear in other disciplines too. So Seymour Papert was who's like a really famous early childhood educator. He would be the apprentice of Jean Piaget, the like pedagogist I mentioned. And then Marvin Minsky had a lot of opinions, the AI guy, about education. And there was just, it seems like there was so much less knowledge that people could have a conversation together, whereas
across
nowadays,
disciplines.
yes, across disciplines, whereas nowadays it's so siloed that the people at the NIPS conference don't necessarily talk with the early childhood educators, and that's a pity. I wish that would return.
We do have an audience question that kind of relates to this. The Grand Malmö wants to know, does Linda Liukas think that we need to have education systems like Hey Ruby to teach humanistic perspectives to kids as well? Because there is a criticism of people who work with tech that they have a lacking understanding of humanist thinking. Should they have a Hey Michel Foucault?
I absolutely think that philosophy, ethics, history is profound in any technology education, at the university level for sure, but even like before that. And like one of my professional kind of dreams or crazy goals is that I want to start like a school someday, and probably the school is going to be a school where you don't actually use a computer before like 3rd grade or something like that, but you practice these thinking skills and stuff like that before. But yeah, I think in order to make more meaningful technology, we need to have more meaningful conversations of what it means to be a human, and that's what we've been having here for the past 2 days.
And I guess what we can take away from this past 2 days is that no matter what our area of expertise, to be able to like even start approaching the kinds of problems that we need to be solving in our lifetime, we need to talk across these boundaries.
Absolutely. Technology is far too important to be left for technologists.
Thank you so much, Linda Liukas.